Aloha. In this video, we discuss mixtures of weak acids. This may sound a little intimidating, but it's easier than it sounds. In mixtures of weak acids, one of the acids usually dominates the proton concentration, and the other ones can therefore be ignored. And that's kind of similar to the way we approached the problem of polyprotic acids. So solving these is going to be similar to solving polyprotic acid problems. And in those, that's where the first dissociation dominated the proton concentration, and then the dissociations that occurred after that could be ignored. So check the last video, lecture 9, if you want to have a look at polyprotic acids first, and you'll see that we approach these similarly. As an example, let's find the pH of a 1 liter solution containing 0.1 moles of HF and 0.1 moles of HClO. So there are two weak acids here, hydrofluoric acid and hypochlorous acid. Hydrofluoric acid, I know it's a weak acid because I can look up its Ka, and same with that. They both have Kas, so that's how I know they're weak. So hydrofluoric acid, the concentration is 0.1 molarity, and same thing with hypochlorous acid, 0.1 molarity. So we need to consider all of the proton sources. Hydrofluoric acid is HF, and it dissociates to give protons, and the equilibrium constant for this equation is 6.8 times 10 to the minus 4. Hypochlorous acid also dissociates to form protons in solution, but its equilibrium constant is only 2.9 times 10 to the minus 8. That's like 4 orders of magnitude less. And you can even consider water if you want. Water dissociates to give protons with an equilibrium constant of the order of 10 to the minus 14, so way less. Now, it's going to be the hydrofluoric acid that dominates here. This is a good rule of thumb that you can use is if the equilibrium constant for the next acid in line is at least 3 orders of magnitude, 1,000 times smaller, then you can ignore it. And this one's 4 orders of magnitude, so you can definitely ignore this. And water's is another 6 orders of magnitude, so that can definitely be ignored. But as we did in the polyprotic acid video, we will demonstrate, that you can ignore this hypochlorous acid by first taking it into account. And so we're going to deal with this, and then we'll see that we didn't need to deal with it. So if you're asked to find the pH of this mixture, just delete that. In other words, find the pH of 0.1 molarity HF. So that's what we're going to end up seeing is how we can approach this problem. So here's the solution. Let's consider the strongest of the proton sources first, the HF. HF dissociates, and here is its equilibrium constant equation. We start with 0.1 molarity, no protons, and no fluorides. So we lose X and gain X here, and here are equilibrium concentrations, and we plug those in right there into the equilibrium constant equation, and then we plug in the Ka right here. This is our equation, and we can solve for X exactly. I would solve it exactly. This is not quite 1,000 times bigger than that, so I would solve it exactly, and your X comes out to 0.007913. Okay, so that's the proton concentration from HF. Now, as we did in the polyprotic acid problem, we can think of the next acid in line as dissociating next. And so after this one dissociates, now that one happens. So the HClO has this equilibrium chemical equation with the corresponding Ka equation. And the initial acid concentration is 0.1 molarity, and now the initial proton concentration is what was provided by the first dissociation. So plug that in right there, just like we did in the polyprotic acid situation, where the initial first dissociation proton concentration was plugged in as the initial proton concentration in the second reaction. So plug this in right there in this second reaction. And so since we don't have any hypochlorite yet, so we have to lose X here and gain X there and there. And those are our equilibrium concentrations. And we plug those in to the Ka equation and plug in the value for Ka. And now we're left with this expression. Now this time you can use the X's small approximation. In fact, you can use it twice. You can ignore X here and ignore X there. And it would make it a lot easier to solve. So X doing that is 3.66 times 10 to the minus 7. So that is the amount of proton gained in the second dissociation. So the total amount of protons so far is what you had at the beginning from the first acid plus what you get from the second acid. But this is 10 to the minus 7, and that's like, you know, negligible compared to what the first one gave us. You know, you would be adding digits way out here. So this proton concentration is rounded to 0.0079. It doesn't make sense to add this number to it. So that is your proton concentration. Now we could go on and consider water as well, but don't bother with water. We're just, you know, shooting ourselves in the foot if we go through that. So that's the point. You know, I wanted to demonstrate that we didn't need to do this. We could have stopped here after we found X. So our proton concentration is that, and we can now plug that into the pH equation. pH is negative log of the proton concentration, and that comes out to 2.10. So that's how you do it. In our next video, we will discuss acid strength and molecular structure. So we're done with ice tables in this chapter. So in this series of videos, we're done with ice tables. No more calculations. So the next two short videos to sum up the series will be, you know, no calculations, just a little more insight on acids. And then the final video will be kind of like a little summary. So stay tuned for the next one, and aloha.